Log on, tune in, find out. Another good idea from Cambridge.
Oh, you mean the design?
So, it's my pleasure to introduce Dariusz, who I don't need to introduce really. Actually, the one thing I just wanted to say about Dariusz, of course, is he, has been an organizer of this with me, but I just wanted to make absolutely clear, if it wasn't evident already, that I am very much the co-organizer, and actually this is down mainly to Dariusz and his organisation. So, really, he's done by far most of the work of the two of us, so very grateful to him for that. But now it's time for his talk, so I need to introduce you no more. Dariusz.
Thank you very much, Andrew. I'd like to welcome you this early morning after the banquet. It must be painful to be here so early, but we must know that an even more painful experience is to be the first speaker after the banquet. I'd like to draw your attention for a couple of minutes to the problem which is my research area, which has been my research area for some 20 years. To start with, let's consider the following example. We have a metal block with a crack inside, and we hit the left boundary of this block to the temperature of 100 degrees centigrade. As for the right boundary, we allow for a constant flow of heat from the block to the air. The top and bottom boundaries are isolated. So, if we look at consecutive snapshots of the temperature distribution, we see that we deal with a special temporal phenomenon. So we observe evolution in time, but we also have evolution in space. So the temperature changes both in time and space. As we wish to have some more insight into the physics behind this phenomenon, it is described by the following heat equation. So this is the so-called partial differential equation, in which you can find the partial derivatives with respect to time t, and we also have second derivatives with special variables, which are represented here as a Laplacian. Such kind of equations must be complemented with initial conditions. We assume here that we hit our block from the temperature 0 at the beginning. This is a similarity to ordinary differential equations, but we also have to complement everything with the so-called boundary conditions. Oh, I mentioned those boundary conditions. So this is a specificity of partial differential equations. In this description, you can see the parameter theta. Theta is the so-called thermal conductivity. Normally, it is a very rare case that we know its value, so this parameter must be identified based on observations. If we have a thermocouple or a pyrometer, we can place it and we can take measurements, and as is usually the case in parameter identification, then we may attempt to tune this parameter so as our model be as close as possible to the observed observations. But the problem which is natural here is where to place this pyrometer. And here we start with the design problem. So processes like this one are very common in engineering practice. You can see on this slide, you can see other examples. And the air pollution monitoring is especially attractive here. I will talk about this a bit later. One of the expected tasks of air protection systems is to provide expected levels of pollutant concentration in a given urban area. But to make such a forecast, the appropriate model is necessary. It usually takes the form of an advection diffusion equation in which only some coefficients are known. For example, we can measure the wind field, but other coefficients, for example, the diffusivity tensor, are unknown and must be identified in a way. So we have similar problems because We have a set of measurement stations which measure the air pollution, the pollution concentration, and the problem is how to place them, how to locate them in a given area. We can use 200 stations placed uniformly, but it turns out that we can achieve the same accuracy regarding the model quality when we use, for example, 20 stations but placed in an intelligent manner. What does it mean, an intelligent manner? You will see in a couple of minutes. So we deal with the so-called distributed parameter system. Evaris Rafajłowicz introduced to this topic yesterday in his very fine talk. So we have a phenomenon which is described by a partial differential equation, which is known up to a vector of unknown parameters theta. To identify this parameter vector, we make observations using sensors. And this is the main subject of my talk, how to choose optimal sensor locations. For a long time, this topic was mostly confined to stationary sensors, but in recent years we have observed a revolution regarding observation of such systems. So we can have a pilotless aircraft, we can use balloons, we can use robots which can carry sensors. So a variety of observation strategies is really very rich now. In my talk, I'm going to focus your attention on some simple matters. I treat this as an introduction to the topic. But I'd like to talk about three main strategies which are omnipresent now. So first, we can use stationary sensors. These sensors are, the positions of the sensors are fixed in space. Then the question is how to locate them. We can use scanning. So we have a number of stationary located sensors, but at a given time moment only some of them are activated. The others remain dormant. The reason for using not all the available sensors, but only some subset of them, is the reduction of the complexity of the whole system, of the cost of maintenance and operation. So the question is, which sensors should be activated at a given time moment? And finally, we have mobile sensors. I will only give a few words about this because this is the subject of the next talk by Maciej Patan. So we have sensors which are carried on mobile platforms, such as mobile robots or pilotless aircraft. And then the natural question is how to design such trajectories. Intuitively, we feel that this strategy is especially attractive because the measurement devices are not fixed and they can track points which at a given time moment provide the most valuable information about the parameters. On the other hand, the design strategies here will be the most complicated. As I have just mentioned, in recent years, we have witnessed a real revolution regarding observation of spatial temporal systems. This is due to advances in miniaturization, networking, and sensing. The convergence of the three topics and advances in them led to a real evolution and the emergence of the so-called sensor networks. As a result, we can use very small devices. Sensor nodes, which are called modes, can be really small, like this, or even smaller. They're called the so-called smart dust. And each sensor node is a kind of a computer. It has a memory, it has some elementary processing capabilities, it has some capabilities to communicate wirelessly with other sensor nodes. So sensors collect data, process them on some elementary manner, in some elementary manner, and then forward these data to base stations. These base stations pass them to the sensor network server, and usually the sensor network server is connected to the internet. In this way, sitting in front of a computer in Cambridge, we can observe that data which are simultaneously collected, well, in the States, in the United States. So it is a reality, not only now, it became a reality several years ago. And sensor networks are really manufactured. Here you can see some companies, well, this is not commercial. And applications, of course, started from military ones. Well, the agency, DARPA in the States, started this research, but now we have more and more applications in our life. We'll have to get used to smart homes, smart motorways, and so on. But if we try to deal with the problem of how to locate sensors or how to activate sensors, the problem is not that young as the problem as sensor networks, because the story started many years ago. You can see here some qualification of the existing approaches. I'd like to focus your attention on the mainstream of works. It is very surprising that I found the first traces of this in a notebook by Ucinski and Fedorov, written in Russian. It's a pity it wasn't translated into English. Very fine book with very bright ideas, as usual, were Valis involved. It was in the mid of 1970s. Then a few works appeared. A great contribution was made by Evaris Rafailovich, and this is not an exaggeration. So he really contributed very much to the development of this area. There is a fine book by Sun, who developed design methods based on optimum experimental design techniques using the optimum design and so on. Very fine book regarding hydrology, how to locate wells. This is a very expensive problem, how to drill a well in hydrology, and he invented some applicable techniques to do so based on the methodology of optimal experimental design. Well, I and Maciej Patan tried to contribute to some extent to this area, well, with more or less success. To be more concrete, let's start by some formal description of our system. So we have the partial differential equation. In the partial differential equations, there you can see the derivatives with respect to both the time variable, with respect to the spatial variables. There is an unknown vector of parameters, theta, and for simplicity we consider only one quantity of interest. This can be, for example, the temperature. We'll call it the state. Here this is the example concerning the advection diffusion equation, which describes the propagation of air contaminant. You can find here the diffusion term. This is the advection term. You can here find the sources of pollution. And in this model, for example, we have the diffusion coefficient with some unknown parameters to be estimated based on measurements. As for measurements, in order not to make things too complicated, we assume a very simple topic, a very simple framework. We have a given set of places where sensors can be placed. So these are allowable sites, and the number of such sites is finite. So this is just as in the case of usually considered in experimental design, where we have a finite set of support points. And then, this may look funny, but we can make such an assumption. For now, I will show you that it is not that stupid. That we can place at one site more than one sensor. So the number of sensors placed at one site is denoted here by Ri. This is not that stupid at the moment because we can repeat our experiment many times, and then if we consider such repetitions, so this becomes meaningful. Normally we make only one experimental run, so in this case really engineers don't believe that this is sensible, and to some extent they are right. As for the output equation, well, we assume that for simplicity we observe the state, for example the temperature directly. The observations are disturbed by noise, represented here by epsilon. The number of sensors, the total number of sensors is capital N. So my intention here is to show you how everything should be reduced to the framework you know very well, to the framework which is considered usually in optimum experimental design. So the index J corresponds to the repetitions. So we have many sensors perhaps placed at one side, so the repetitions are denoted by like this. So we are in the usual framework of the least squares criterion. We minimize it, and the natural question is how to determine the numbers of sensors placed at individual points. We have a fixed number of known allowable positions, so as to maximize the identification accuracy. What is it? Well, for you it is obvious. We base on some ideas from statistics, the usual Kramerau inequality, and in this inequality we find the information matrix. What is it in our case? After some algebra we can derive the following form of this information matrix. So we have to calculate the integral over the observation horizon, the integral in time, and in order to compute the individual elements of the information matrix, it is necessary to know how to compute the so-called sensitivity coefficients, which are the derivatives of state with respect to the parameters. It is the problem which is widely known, for example, in shape optimization in mechanics. So I learned many things from mechanical engineers, and they elaborated a number of methods which are widely used in practice. Roughly speaking, in order to compute sensitivity coefficients, if for example there are three parameters, apart from the original state equation, we should solve other three partial differential equations. So the calculation of the sensitivity coefficients is reduced to solving partial differential equations. But this problem has become a routine in recent years. There are a lot of software solutions to do so. So this is not an interesting topic to talk about it now. And the rest is the question of introducing the appropriate optimization criterion, the appropriate design criterion to be minimized here. Of course, we can have the optimum design, we can have the L optimum design, and designs here are as follows. This is a table in which the positions of the positions here, the coordinates correspond to the known coordinates of the sites where sensors can be placed. And here you have the weights. We don't use Ri. It is much more convenient to introduce the weights Pi, which are related to Ri as follows. We divide Ri's by N. In this way, this resembles a discrete probability distribution. So, but this is also obvious to all of you. And the question is how to deal with this problem. Well, unfortunately, the quantities, the weights we have here are integer multiples of the reciprocal of the total number of sensors. So we have it with a combinatorial problem, which is not very easy to solve. So the usual procedure is to relax this assumption. Instead of discrete values of Pi's, we relax the problem and we consider as weights all numbers from the interval from 0 to 1. And the weights form in this way the so-called canonical simplex. So the ultimate formulation looks like this. We minimize some criterion defined on the information matrix. The information matrix depends on the design, that is to say on weights, and we wish to find weights which minimize the whole stuff. And this is the information matrix. Well, what follows, I will use the following quantities. This is the derivative of the criterion with respect to matrix arguments. This is also the stuff you know. For example, this for the d-optimum criterion, this will be the negative of the information matrix. So based on this quantity, we can define functions c and phi, and then we can formulate optimality conditions. We can find characterizations of optimum design. So this is just another application of classical optimum design theory. Nothing new. As for numerics, because based on optimality conditions, we can only characterize optimum solutions, but the question is how to find such solutions. There are also a plethora of techniques. As for computing, for example, the d-optimality, in recent years, we have observed big progress regarding convex optimization. And my objective here was to invite here to Cambridge Stephen Boyd. Well, he was too busy to come. He is, well, maybe the person who contributed the most to this topic. So we can reduce the problem to linear matrix inequalities. There are a lot of solvers who can treat this problem directly. Here the trick is to introduce some new auxiliary variable q. Then everything is reduced to the formulation where solvers of related to linear matrix inequalities can be used. What is more, we can treat in this way even the e-optimality criterion. Normally, it is a very difficult criterion because it is non-differentiable. We can also do it using linear matrix inequalities. Finally, as for the d-optimality, it's a pity Ben Tosny is not here, but he listened to my talk on it some time ago. We can use his multiplicative algorithm. So it is not a problem. So everything is known. And as for illustration, we have, for example, here a metallic core with a rectangular crack inside. Everything is static in time. So we neglect the evolution in time. In this example, the left and right boundaries are subjected to constant voltages, which force the flow of a low density steady current. And this current can be described by the following Laplace equation. In this equation, we can plug some sensitivity coefficient. We use model-based design. That is to say, we assume some form of this conductivity coefficient. We know the functional form, but we don't know the parameter values. We use the local design, so in order to maximize the determinant of the information matrix, we should assume some nominal values for those parameters. The result is like this. So here the dots denote the allowable sensor positions, and here you can see where to put sensors. So for example, 1/4 of the available sensors should be put at this point. So this is we can interpret the results like this. Of course, everything depends on the criterion which is used here. So the weights can be changed. Well, and the natural question is how to use it, how to implement this in practice. Because for an average engineer, when I suggest him, well, at one point you should put 10 sensors. So well, he will kill me with laughing. And it is possible from time to time. If you have a plate, well, we can put one sensor from above, the other from bottom. Well, but we can also interpret the results as follows. The weights quantify the importance of individual regions. So this is one thing which can be helpful for engineers. Another interpretation is we can put one more precise measurement device at a given point. So this is the interpretation of weights. Finally, I saw some works in robotics. I'm also involved in some research in robotics, where the authors interpret weights as measurement frequencies. If the weight is bigger, so the frequency of measurements must be higher. And finally, we can adapt. It turns out that we can adapt all the stuff I've just described you to the situation when the coefficients Ri are binary, either 0 or 1. But in order to have some variety, let's illustrate this approach for the case of scanning observations. In scanning, we have a number of allowable sites. We assume that at those sites sensors reside already, and the question is which sensors should be activated. So we divide the time interval into, we partition the time horizon into sub-intervals, and the question is which sensors should be activated during each time sub-interval. So this is our problem. So this is the motivation. The problem is combinatorial in nature. If you want to check all the solutions and then to pick up the one which maximize the determinant of the information matrix, you fall into serious difficulties. For example, if we have 1,000 of sites, among which we want to activate 500 sensors. This is the usual framework when we use big sensor networks. And we divide our time horizon into 10 stages. Assume that we have a computer which is able to check 1 billion situations per second. Then you must wait for the result 10 to the power of 3,000 years, so this is really for someone very patient. So the question is how to overcome this difficulty. So this is the usual framework when we have combinatorial problems, but people from computer science tried to invent some tools to overcome such difficulties. Well, we deal with computer science from time to time, so we adapted their approaches, and here is some result. So at this time, when we have the output equation, this can be written down as follows. At the stage k, let's remind that we divided, well, you see here, the observation horizon into sub-intervals, and each sub-interval is called a stage. Here is the stage 1, stage 2, stage 3, and we associate with each sensor and each stage the flag called denoted here by VKI. This flag is called flag because it takes two values. One, if the sensor at a given site over stage TK is active, otherwise is 0. So we have binary variables, and for us they are decision variables. The Fisher information matrix takes the following form, and here you have contributions from individual sites. So each site at a given time stage can contribute to the information matrix by this term, and if it contributes or not, we decided by using this flag, which is 0 or 1. Well, G denote the sensitivity coefficients. We complicated things because in sensor networks, sensors, individual sensor nodes have energy supplied by batteries. And well, if you have a mobile phone, well, this mobile phone can't work for weeks or years. You must charge the batteries. So a similar thing is observed for sensor nodes. They have energy from batteries, and a natural limitation here is not to have such a situation. This solution is not satisfactory. These are the number of sensors, and this is their activation times. So this sensor is not used all the time. It's rather lazy, but this sensor is overwhelmed with observations, and which is not very good because it may exhaust its battery. So a better situation is like this, when all sensor durations regarding work are uniform. So we can impose here some constraints regarding activation times. Luckily, they are linear. And finally, we arrive at this formulation. We wish to minimize some criterion defined on the information matrix, subject to this constraint regarding the maximum time of activation, and we impose an additional constraint regarding a minimum number of sensors which are activated at a given stage. Unfortunately, in this formulation, the variables are binary 0 or 1, which complicates things, as we have just seen. How to find a way out of this trouble? We applied, I and Maciej applied the idea which is related to the well-known branch and bound technique. This is a technique invented in the 1960s, very old, but very fine. In many domains, it works really, really fine. And, well, this slide is not good. This will be, but, so, you have the so-called branch and bound tree. We start from our problem in which all the variables are relaxed. That is to say, instead of values 0 and 1, we allow them to take values in the interval 0 to 1. And then this branch denotes that we take one variable and we decide if it has to take the value 0 or value 1. So let's say here we set the value of the first variable v1 as 0, here as 1. And we can continue this in this way. Finally, when we have here at the bottom some terminal nodes, these terminal nodes correspond to all solutions to our problem when all variables are fixed to either 0 or 1. And if we are naive and we wish to check all the solutions, then we have to check all the terminal nodes. But the branch and bound technique is intelligent in this way that at each node we can control the search process, and if we have an oracle which is able to tell us if it's worth or not to explore a given subtree. And the question is how to invent such an oracle. Well, the question is, I don't have time to show you details, but the answer is that we can apply here a technique which is called simplicial decomposition. Roughly speaking, it reduces to a sequence of 2 stages which alternate. At first stage, we solve a linear problem which has an explicit solution. In the second stage, surprisingly, we use, for example, a Ben-Storsney algorithm with weight multiplication. So we can apply techniques which are used by all of you regarding approximate designs in order to solve those combinatorial problems, but we use such algorithms as submodules, as some components. So it is possible. So here is the result regarding some transport chemistry process. We have in the description we have two sources of pollution, and the question is how to find the positions and how to find their intensities. So this is a model, a Gaussian-like shape for the action of each source. This is an advection diffusion equation, so we also have some wind. So here you can see the spread of the pollution concentration. The arrows denote the wind directions, and here you can see active sensors. So it changes dynamically. It follows the evolution of the systems. We have here 100 sensors selected from Maciej knows. Maciej is preparing for the next talk. So. 1,000. So here you have a similar thing, but we use 50 sensors. So the same process, but the number of sensors is low. Well, I must arrive at conclusions, but before, Maciej can wait for a little while. One more problem, this time concerning moving sensors. Maciej will give you more insight, more details about it. But for me it is interesting because it is non-classical to some extent. If we have a robot which carries sensors, it is also supplied with energy from batteries. And the question is, it mustn't work too long. Otherwise it will stop and it will do nothing. So the question is how to minimize the time of action of this robot. And the problem here is that we have our spatio-temporal process, which is defined from the interval from alpha to beta. So we have a big interval. We have a big interval. And the evolution of the pollutant concentration is defined over this interval from alpha to beta. But we wish to select the best interval from this subinterval from this interval where measurements should be taken. So first we must select where to start measurements, and the next thing is how long we measure. So this is a minimum time problem. Of course we measure the state along sensor trajectories. So here you can find this form of the observations along system trajectories. Of course, if we use moving devices, we should introduce some form of the dynamics. This is common for roboticians. So, well, but I don't want to guide you through this way. We don't have time for this. There are some good models devised by roboticians, so they can be used here with including non-holonomic constraints and so on. They can be described as the following equation, set of ordinary differential equations. In this description you can find S, which collects all of the positions of all sensors we have. The sensors, the vehicles carrying the sensors, are driven by robots, are driven by the motors, and the motors should be steered. And here you represent the controls applied to the motors. They can be, for example, voltages applied to robot wheels. And logically, the controls should be bounded. This is also a necessary condition if we wish to prove some existence results for optimal control and so on. Of course, if we have several robots, it is natural that they mustn't collide. So we should introduce some constraints regarding the lack of collision avoidance. Another thing, we may have some constraints that must be obeyed, that robots should stay in some described regions, some predefined regions. They can't move from these regions and to measure somewhere else. So this can be described by some state constraints. And finally, the Fisher information matrix. But of course, if we ask the question, how to minimize the time. At this moment, if we have only this criterion that we wish to minimize time, the obvious is the solution is obvious. The time should be 0. We don't measure anything. So this is the minimum value of the criterion of the time optimum criterion. But we wish to measure anyway, and at the same time, we wish to guarantee some guaranteed measure of precision for the estimates. We introduce this precision as a constraint using the so-called d-efficiency, which is defined as follows. In the numerator, you have the determinant of the information matrix for the current interval, subinterval, for the current trajectories, but in the denominator, you have a baseline, let's say, that is to say, the value of the determinant of the information matrix, which corresponds to the best trajectories, but for the whole time interval. If we shorten the interval, of course, the value of the determinant of the information matrix will be lower, and in this way, the efficiency will be also lower. It won't be 1. So, we should introduce a constraint that the efficiency should be no less than a given prescribed value, for example, 0.8. So we include the accuracy of parameter estimates as an additional constraint. And finally, we arrive at time optimum formulation in which we minimize time subject to constraints regarding collision avoidance, subject to constraints regarding the guaranteed efficiency, and we look for optimum trajectories, optimum controls, and for optimum initial sensor positions. I don't have time to show you some details regarding numerics, regarding algorithmics, but in fact, you will need at least one semester, of course, of optimum control. So maybe let's skip this topic. Everything can be reduced to a formulation after some turning up, after introducing some auxiliary variables. Stefan, we must discuss about it after my talk. We can reduce this to a classical setting where some off-the-shelf solvers can be used. We have experience with some fine solver for optimum control problems, which is called RIOTS, written by my colleague from United States, Yang Pan Chen, from Utah State University. So you can here find some example optimum sensor trajectories when we can observe over some time interval, and this is the same when we sacrifice some optimality, some degree of optimality, we impose that the efficiency should be no less than 0.8, and of course, instead of the interval from 0 to 1, we start measurements not at 0 but almost at the half of the interval and continue till the end of the interval. The trajectories are changed, but you can note here that the sensors work only for half of the time which would be used in the previous case. So it is a benefit. So this is the end, and time for conclusions. This is an ongoing work. I must mention some of my collaborators. We applied some optimal experimental design techniques to Kalman filtering using some properties of covariance matrices for filtration error. That it is possible to reduce, in some cases, the problem to the setting which is usually used in optimal design techniques for A-optimality, for example. We try to implement everything on a real platform with our collaborators from France, Professor Laurent Autric. I have two bright PhD students who defended their thesis. This regards parallel algorithms, because such problems require some big computer power. So we parallelize algorithms in clusters of computers, and we are about to finish a book published by Springer about this. And finally, this is the beginning of the story, really, because all I've just mentioned to you, this concerns the past. The real story begins here when we use decentralized approaches. Because in sensor networks, we have a situation when individual nodes don't know about the whole situation, the global situation in the network. They have information from neighboring nodes, and the question is how to steer their activities in order the system organize itself in a way that, well, the accuracy of the estimation will be the higher. So this is joint work with Maciej Patan. And this is some advertisement for my book, which was published a long time ago, but well, some material is still up to date. Thank you very much for your attention.
I have a question concerning your branch and bound approach. What is your experience with the relaxations? Do you need to branch a lot, or do the relaxations already give very good solutions?
The algorithm works very fast on a very bad laptop. I have my favorite laptop is 10 years old. I use Unix on it, and it works immediately because of one thing. If at the beginning you use a completely relaxed problem, and then you round the solution, you obtain one of integer value solution. This gives you, in most cases, a very good estimate of the best solution.
The integrality gap is not
Exactly.
not big.
So
This is my
fine.
experience also. Usually relaxations, they already give integer solutions even.
But
I think
if
there's
you
a
apply
reason from statistics that this is the case, that you have an exact design of whatever this is called.
So I don't think you said this explicitly, but I was imagining that all of your sensors are of the same type. They're all the same modality. Is that right? And I wondered if you were extending to a case where you had a collection of different modalities, could you do some sort of optimal thing in a single framework, or would you, excuse me, do sequential, somehow place all the acoustic sensors and then place all the optical sensors?
Well, this would complicate things to some extent, but because you have information from different sources, so we should, well, fuse this information in a way. One thing which seems promising in this context would be to use a Kamel filter. Well, we work on this with microgeometry, but with some results which are not very good for publishing now. This is beginning.
Sorry. I had a question regarding the trajectories you compute for these mobile sensors. Is this a well-posed problem? Do you observe oscillations if you take a small discretization?
Yes, you're absolutely right. You're absolutely right. As for identification of distributed parameter systems, the problem is that you have inherently ill-posed problems. So if you want to have a fine setting, in the literature people write that sometimes 7 or 8 parameters is the maximum when you can deal with this problem with a well-posed setting. If the number of parameters is higher, you immediately fall into the trap of ill-posed problems. So when you wish to estimate the parameters, you must do regularization in a way. Otherwise, it fails.
And the trajectories, do they tend to oscillate, or do they tend to be?
Yes. Trajectories, no, because as for planning, we don't consider equal problems yet. So we take the original problem without the regularization term.
In these problems, particularly where you're doing plume modeling, we did some work on plume modeling for the Chernobyl cloud, for example, and it seems to be a drift towards using particle filter methods for data assimilation, as opposed to extended Kalman filter. So I wondered if somehow there's a new subject which is the combination of experimental design with the more modern particle filter, less Cameron filter as well. And does the choice of design somehow help with this innovation?
You're absolutely right. So I have two PhD students who work with Kalman with particle filtering in fault detection for robots, and we try to find some ideas for experimental design with some minor results for now. But you're absolutely right at that. This will be.
One last question.
Just a comment. There's some work by people in Newcastle, Adrian Wills, on experiment design based on quantum
Which group in Newcastle?
Uh,
Geophysics? No.
No, the Graham Goodwin's group. I had one question actually. So can you
That's
take dynamic?
Newcastle, Australia.
Yes,
Oh,
yes. Sorry. Yeah, sorry.
No,
So can you take the dynamics of the sensor movements into account?
Exactly. So in this simple example, we steered directly sensor velocities. So it was only kinematics, but I published one paper regarding a more complicated dynamics for a differential drive robot with non-holonomic constraints. So the results are quite similar. It is possible. So it doesn't impose any constraints.
Okay, thank you very much indeed.